Right. Next, I mentioned we were on the 1-year anniversary of a NASA satellite, and the satellite is called the Transiting Exoplanet Survey Satellite, or TESS. So it started. It was actually launched more than a year ago, but it officially started its observations in the summer of last year. And many of you have probably heard of the Kepler spacecraft, and the Kepler spacecraft used a different technique from the radial velocity method, something known as the transit technique, and TESS does the same thing. So TESS is a spacecraft that is the successor to Kepler, and this is an explanation of how the transit method works. And basically what you're relying on is a planet that's orbiting with the plane in our line of sight. And as the planet passes in front of the star, you actually see a dip in the brightness of the star. And so over time, depending on how big this dip is, you get an idea of how big the planet is relative to the diameter of the star. And so you can, knowing from our stellar evolution models how big stars are of different spectral types, we get an idea of how big the planet is. And depending on how quickly the planet is orbiting, and also from our models, we have a good idea of how big the diameters of the stars are. We get an idea of how far they must be orbiting, and so their orbital periods. And so this transit method actually can tell us a lot of information about these planets. And so what Kepler did was the Kepler spacecraft is still in operation, but it basically stared at one part of the sky over the last 10 years. And actually, its control wheels started failing, and so now it's in a separate phase of its mission where it's actually looking at different parts of the sky as it's orbiting the sun. But during the main primary part of its mission, it basically stared at the same patch of sky repeatedly and looking for points in time when the starlight would dip by a very small amount, usually less than 1%. And if it caught these multiple dips, astronomers would then try and confirm using ground-based telescopes whether these stars, in fact, actually did have planets or not. But TESS does something different. It actually maps pretty much the entire sky. But what it does is it has these giant cameras, these giant CCD cameras, each of which records about a 24 by 24 degree area, and there are 4 of these cameras, so they actually observe what they call one observation sector, and each of these sectors is observed for about 27 days at a time, and then after it observes one sector, it moves on to the next sector, and then as you can see, it spends about a year observing one hemisphere of the sky, and then it goes on to the other hemisphere, and pretty much it's observed the entire sky, and you can also see that it overlaps with with some of the Kepler fields, but not. And what's also really important is that the polar regions are observed continuously. And what's nice about that is that because it's mapping those polar regions, we're going to get a lot of information about planets in those polar regions because the TESS spacecraft has effectively observed them continuously for a year. And so when the successor to the Hubble Space Telescope, the James Webb Space Telescope, that's the telescope we saw right at the end, launches finally, we think in the year 2021, it will have this bounty of planets to observe and follow up with. So here is a synopsis or a summary of what we just saw. These are each of the 24-degree wide camera views, and there are 4 of these at any given time. And so you're observing these sector strips, which cover, basically from close to the equator all the way to the pole. And over the course of a year, it covers 1/2 of the sky. TESS basically finished observing the southern sky, and it's currently in the middle of observing the northern sky. And so over the course of 2 years, you'll have complete coverage over the entire sky. And then it's aligned in such a way that it's ignoring the the ecliptic, the plane of the solar system, just because there's planets and comets and asteroids and other objects that make it confusing. So it's avoiding, that's the zone of avoidance there. And here are just some pictures showing how big the field is. So there's actually 4 CCDs, each of which is 12 degrees across. And as we zoom out, you can see that there's actually 4 CCDs together that make up the 24-degree wide detector. And each of these is basically big enough to cover a relatively large constellation. And so here is the constellation of Orion mapped onto the footprint of those detectors. And there are different types of observations. So it doesn't necessarily send all the data back from those detectors, but what it does do is that every 30 minutes or so it will send everything back. But at shorter time scales, the satellite is focused on 200,000 stars that the primary scientists figure are really important for looking for planets. So they are observed every 2 minutes instead of every 30 minutes. And then there are also some stars where they're observing every couple of seconds, where they're looking at basically very rapid variations in the light of the star. Now, the first story involving TESS is about a paper that just came out, and it was actually the discovery of 3 planets orbiting this one particular star, TOI 270. And all the stars that I'll be talking about are what are known as red dwarfs or M dwarfs. And these are stars that are much less massive than our sun. So they're smaller than our sun. Instead of glowing with radiation peaking in the yellow part of the spectrum, they tend to peak towards the red and the orange. And so they'll look reddish to our eyes. And because they're much less massive, that means stars, or the planets that orbit them, will tend to orbit closer, and the habitable zones of these stars are also much closer in. So the zones in which on the surfaces of rocky planets, it's neither too hot nor too cold for liquid water to exist. Sort of another name for these is the Goldilocks zone. And so these are the places where potentially life as we know it could exist. And so in this particular system, they've diagrammed the locations of the 3 planets that have been discovered relative, and we put in the Jupiter system with Jupiter's 4 large moons and some more distant moons, just to give you an idea of the scale. So this solar system is much smaller than even the orbit of Mercury. It's basically the size of Jupiter's moon system. And here is the data. So this is the light curve. And these color dots basically represent the points that occur during the transit when the planets blocked the light from the star. And as you can see, so here are the transit data from those 3 planets. And if you look at this, this is 100%, and they've kind of shifted these. But the amount of starlight that changes is much less than 0.1%. It's order of about 0.1%. So that tells you, I mean, this is the reason why you have to go out into space, because stars twinkle in our atmosphere. The atmosphere refracts and changes the amount of light that we get from the star. But if you can put a satellite above the Earth's atmosphere, you get really good observations that allow you to detect these very subtle changes in the starlight. This just shows a plot of where astronomers modeled the masses of the planets, and they basically show you that depending on different types of compositions of planets, these planets could conceivably be Earth-like, or they could conceivably have different amounts of rock versus water. But this is the innermost one is the most Earth-like, meaning it's only about 1.25 times the size of the Earth, and but it's so close to its parent star that the surface is very, very hot. So about 490 degrees Fahrenheit, whereas the other two worlds are about 2.5 and 2 Earth radii in size, and they are potentially much more temperate. And what's interesting about these two other worlds is that they're bigger than the Earth, because they're at least twice the size of the Earth, but they're not as large as Neptune or Uranus. So in our solar system, there's no planet that's larger than the Earth and smaller than Neptune, which is about 4 times the diameter of the Earth. Whereas here, and we're starting to, these are 2 planets that are sub-Neptunian, but also larger than the Earth. And these provide interesting targets in the future for follow-ups to help understand more about these sub-Neptune planets.